2 cables holding down a multi-ton ship, 3 unknown directions, and 1 Cartesian system. If these spatial forces look so messy that you can't even tell which way they're pulling, relax. We are going to strip them down, wire by wire, and completely shut down these complex 3D structures. I'm your engineering muse today. We are wrapping up 3D spatial resultants. Just remember our golden rule: force follows the path. Pack them into the IJK boxes. Once you pin down those coordinates, the rest is just tossing components into their designated storage organizers. Today's menu covers problem 2101, the 2 stern mooring cables, and problem 2103, which features some nasty geometry at the suspension point. Don't panic. The underlying DNA of both problems is identical. Identify coordinates, find position vector, extract unit vector, multiply by force magnitude, sum the components. Here is my 3-second rule. The moment you see spatial members or cable geometries, bypass everything else, go straight down the position vector route. Period. But here is the catch. In 2101, you can read the coordinates right off the diagram. In 2103, you have to decompose an angle just to find the coordinates first. And that single step, it filters out half the class. All right, let's look at problem 2101. What's the giveaway here? We have 2 cables running from point C at the stern to mooring post A and B on the dock. The force directions are dictated purely by geometry, and we need the magnitude and coordinate direction angles of the resultant force. This is a textbook coordinate to vector workflow. First, let's establish the origin. We'll set it at C. Why C? Simple, because every single dimension in the prompt is measured from the stern. Setting C as your origin means your position vector perfectly matches the endpoint coordinates. Boom. You just skipped an entire subtraction step. That's a pro engineer habit right there. Not some extra condition. Let's read the anchor coordinates in feet. For point A, we go 50 along the x-axis, 10 along the y-axis, and minus 30 along the z-axis. For point B, we have 50 along the x-axis, 10 plus 40 equals 50 along the y-axis, and minus 30 along the z-axis. Now, watch the signs closely. Both anchor points sit lower than the stern. This means their z components must be minus 30. This is where most people drop points. Seriously, sketch it out before you write. Don't just trust your gut. Since force follows the path, the line of action for the cable tension points directly from the origin C toward the anchor points A and B. Let's write down the position vectors. Next, we need the magnitudes. Now, we strip them down to unit vectors by dividing the position vector by its scalar length. Quick 5-second check if the calculated result equals 1, perfect. The 3 components of a unit vector are literally the direction cosines relative to the axes. Let's scale them up into Cartesian force vectors by multiplying the force magnitude by the unit vector time to open our component organizers. We sum the x, y, and z components independently. This is the real power of the Cartesian system. Let's find the total magnitude of this resultant. We'll report it as 338 pounds to keep things clean. Finally, the coordinate direction angles. Don't rush this. Calculate the cosine first, then hit inverse cosine. Look at gamma equals 118. That means cos gamma less than 0, which tells us the resultant force is pointing downward along the z-axis. Since both cables drag down and away, the physics makes total sense. Let's run a quick validation check using our cosmic compass hack. If this doesn't equal 1, you messed up somewhere. It takes 5 seconds to debug. Moving on, let's look at problem 2103. This one is a completely different beast, and honestly, the real bottleneck here is geometric modeling, not the statics itself. Look at the setup. We have 2 cables, AB and AC, pulling from a shared suspension point A. Now point B is nice and cooperative. You can read its coordinates right off the grid, but point C, it's buried inside a nasty 20 rotation in the XY plane. You have to translate that messy geometric configuration into clean coordinates first, or you're completely dead in the water. To keep things absolutely foolproof, let's not mess around with relative offsets. We're going to use the main origin O as our single source of truth. Every single point will be measured from this absolute anchor. No guessing games. Let's pin down the absolute coordinates for our 3 critical points. First, point A, or a suspension source. From the origin O, we don't move along the x-axis at all. So XA equals 0. Look closely at the drawing. It moves backward along the negative y-axis by 2 foot. So YA equals minus 2. Then, it climbs straight up the vertical pole by 4 foot. There you have it. Next, point B, the end of the first cable. From the origin, it pops out 1.5 foot along the x-axis, stretches out minus 3 ft along the y-axis, and sits flat on the ground. meaning ZB equals 0. Now, let's tackle point C, and please pay attention because this is the ultimate landmine. See that blue triangle? Let's map out a mental trajectory. Imagine point C started as a 2-foot clock hand pointing straight down the positive y-axis. Now, rotate that hand 20 to the left toward the negative x-axis. Since it's a rigid rotation around the origin, the length stays exactly 2 foot. That never changes. So after the swing, we project it using basic trig. Along the x-axis, it swings into negative territory, so it is minus 2 sin 20, which gives us minus 0.6840 foot. Along the y-axis, its shadow on the positive side is 2 cos 20, which is 1.8794 foot. And it's on the ground. So ZC equals 0. Put it together. Once you have these 3 absolute coordinates, you can completely turn your brain off and just run our formula. Position vector equals tip minus tail. The rest is just simple subtraction. Even a pro can't mess this up. I know plenty of students who stare at this diagram for an hour trying to figure out why the y-span is 3.88 foot. Let me break it down for you. C is at 1.88 in the front, and A is at minus 2 in the back. The absolute span between them, 1.88 minus 2, equals 3.88 foot. Boom. That's the beauty of absolute coordinates. The math does the thinking for you. Let's write down the position vectors. First step from here, magnitudes. Let's punch them in. Next up, unit vectors. We just divide the position vector by its scalar length. Quick 5-second check on UAB if the calculated result equals 1. Perfect. Now, let's grab the force magnitudes right off the diagram 20 pound and 40 pound and scale them up into Cartesian force vectors. Time to open our IJK component organizers and sum them up horizontally and vertically. Let's find the total size of this resultant force. We'll call it 52.2 pound for the final answer. Finally, let's extract the coordinate direction angles. Don't rush this. Jet the cosines first, then hit inverse cosine. Look at alpha equals 87.8. That means the resultant force is almost perfectly perpendicular to the x-axis. Why? Because the 2 cables pull against each other along x and pretty much wipe each other out. And gamma equals 154. It is a massive obtuse angle, meaning the force is slamming straight down into the ground. Both cables are anchoring it down. So the physics makes total sense. Let's do a quick final check with our cosmic compass identity. It's 100% bulletproof. Let's take a step back and look at how these 2 problems stack up against each other. It'll help you spot the traps on an exam. If you want to survive any 3D spatial force problem Hibbeler throws at you, stop guessing. Just run this exact script every single time. First, lock down the grid. Look at the axes, verify the positive directions, and don't trust your instincts. Second, hunt the coordinates. If they give you direct dimensions, write them down. If they throw an angle at you, isolate the 2D plane first, use sin and cos, and lock in your XYZ data. Third, build the position vector. It is always position vector equals tip minus tail, end minus start, every single time. Fourth, find the length. Get the scalar magnitude by taking the square root of the sum of the squares. Fifth, strip it to a unit vector. Divide the vector by its magnitude. And look at me. Verify that the squares sum up to 1 right then and there. Catch the glitch before it catches you. Sixth, inject the force. Scale it up by multiplying the scalar force by your unit vector. Seventh, sum them up. Combine your I, J, and K components into their separate storage boxes to find the total resultant vector. And eighth, get the final answers. Calculate the magnitude, solve for the direction cosines, and use inverse cosine to get your angles. Double check that your squared cosines sum up to 1, and you're done. Let's wrap this up with one simple truth. A 3D force vector is just a position vector divided by its length and multiplied by the force size. That is it. It's literally just an engineering hack for direction cosines. Here's my parting advice. Whenever you see a structural cable or a brace tilted at a weird angle on the ground, do not panic. Drop it onto the flat XY plane first, split it up, and treat the height Z as a separate issue. You are basically chopping a scary 3D problem into 2 simple 2D steps. Remember our 3-second rule. The moment you see a spatial member and some geometric dimensions, go straight for the position vector, throw those components into the IJK boxes, and the whole problem collapses into elementary school addition. Watch out for the negative signs on the z-axis when things point down, don't swap your sines and cosines on the geometry, and always validate your unit vectors. And look, if your direction angle comes out greater than 90, relax. It's not an error, it just means the force is pulling against that axis. Trust the blueprint, trust the math, and I'll catch you in the next lesson.